Hi guys, welcome to lesson 12.8, probability of compound events, the final lesson in algebra. Our objective for today is that I can find the probabilities of mutually exclusive and overlapping events, and that I can find the probabilities of independent and dependent events. Now, a compound event is made up of two or more events linked by the word and or the word or. Mutually exclusive events are two events that have no outcomes in common. Overlapping events are then the flip side, where they have at least one outcome in common between them. Independent events are when the occurrence of one event does not affect the probability of the second, and dependent events are the outcome of one event affects the probability of the second. You can write the probability of a compound event as an expression involving probabilities of simpler events. This will make the compound probability easier to find. So the first thing we want to look at is the probabilities of A or B happening. So if they are mutually exclusive, we are going to add the probability of one event plus the probability of the other. If they are overlapping, we do the same thing. We add the probability of one event and the probability of the second, but then we need to subtract the overlapped. The probability of the overlap. All right, so suppose you spin a spinner that has 20 equal sized sections numbered 1 through 20. What is the probability that you spin a 2 or a 5? So these are mutually exclusive. You have 2 and 5. There's no overlapping pieces there. So the probability of spinning a 2 would be 1 out of 20. The probability of spinning a 5 would be 1 out of 20. So the probability of spinning one of those two numbers would be a 2 out of 20, which reduces to 1/10. Okay? That would be your final answer. Now, what is the probability that you spin a number that is a multiple of 2 or 5? Well, let's just list those out real quick. Multiples of 2, those are even numbers. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. And multiples of 5, that's going to be 5, 10, 15, and 20. Ooh, look. We have two overlapping numbers. 10 and 20 appear in both data sets. So now we need to calculate our probability. So we use the probability of A. So the probability of getting a 2, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 of the 20 outcomes are multiples of 2. And then we're adding 1, 2, 3, 4 potential outcomes that are multiples of 5. And then we need to subtract our overlap. Now the overlap was 10 and 20, so two of the numbers overlapped. So 10 plus 4 minus 2 is 12 over 20, which reduces to 3 over 5. Okay, now I want you guys to try C and D on your own, and then I'll go over it. So letter C, suppose you roll a standard 6-sided dice. What is the probability that you roll an even number or a number less than 4? So even numbers, well, that's 2, 4, and 6. Or a number less than 4, that's 1, 2, and 3. Okay. Now we have an overlap here of the 2. So we're going to add the two probabilities, 3, 6 plus 3 sixths minus 1/6, the overlap, is going to be equal to 5/6. Now, does this make sense? Our possible solutions that would be either even or less than 4 are 1, 2, 3, 4, and 6. So the only number that you would roll that would not be one of your favorable solutions in this would be a 5. So it would be 5 out of the 6 possible choices. Okay. What is the probability that you roll a 2 or an odd number? So we have 2 and odd numbers. We're rolling that same dice. So it's a 1, a 3, or a 5. So this is mutually exclusive. We have 1/6 plus 3/6. And that's going to be 4/6 or 2/3 when you reduce it. Now, the question you're probably thinking, or you might be thinking, is do we have to reduce? Yes. You have been taught to reduce fractions in, I don't know, 5th grade. By this point in your life, you should assume that any fraction you have that can be reduced should be reduced. All right. Finding the probability of independent events. Now, these are two completely separate things happening, and you want to know what happened. So in example 1, you roll a red dice and a blue dice. What is the probability that you roll a 5 on the red and a 1 or a 2 on the blue? Now, when you roll 2 dice, did the outcome of this one have anything to do with the outcome on this one? No. They are two separate things. Probability of one dice and the probability of another are two separate probabilities. What you need to do then is multiply them together in order to get your actual probability. So rolling the red dice, we had a 5. We wanted a 5 on the red dice. So that's 1 out of 6 possible examples. And we're multiplying that by, on the blue dice, a 1 or a 2. So that would be 2 out of 6 possible examples. Multiply them together. Remember, multiply across the numerator. 2 times 1 is 2. 6 times 6 is 36. So we have a 1 in 18 chance of getting that exact combination of a 5 on one of the dice and a 1 or a 2 on the other. Okay, so now suppose that you roll a dice and flip a coin. What is the probability of rolling a number greater than 2 and flipping heads? So we have a number greater than 2 on a dice. What are our possible combinations for that? Well, that'd be 3, 4, 5, or 6. Greater than 2. And we're flipping a coin, and we want to know if we flip heads. Well, a coin has 2 sides, so that's 1 out of 2. So 1 out of 2 times 4 out of 6 is going to be equal to 4 out of 12, which reduces to 1/3. Okay? We have a 1 in 3 chance of that happening. Now, problem 3 is dealing with selecting with replacement. What with replacement means is you are going to take one of the tiles out of the bag and then you put it back in so the number and the type of your possible outcomes has not changed. You're just doing repeated trials of the same exact conditions. All right. So I want to know if I choose a tile at random for the game and replace it and then take a second, what is the probability that I take a dotted tile and a dragon tile? So we have 1 dotted, 2 dotted, 3 dotted, 4 dotted out of 3, 6, 9, 12, 15. So that's 4 out of 15 are dotted. And then how many are dragons? 1, 2, 3 dragons. So it'll be 3 out of 15. Multiply them together. 4 times 3 is 12. 15 times 15 is 225. And that can reduce to 4 over 75. Okay. So the probability of getting that exact combination is 4 out of 75. Now, what is the probability that you choose a bird and then a flower? So, birds, there's 1 there, 2 there, so we have 2 out of our 15. times a flower is only 1 out of 15, so that gives us 2 out of 225. Okay? Now, problem number 4 is going to be selecting without replacement. So what this means is you take one of the tiles out and then you do not add it to the bag. You do not return it to what you're selecting from. Okay, so you choose a tile at random. You want to know what is the probability that you choose a dotted and then dragon. So the same scenario as before. But this time, after we pull the first tile out, it does not go back in the bag. So for a dotted tile first, we still have the 4 possible outcomes. It would be 4 out of 15. Now, for the second possible outcome, or the second pull, we still have the 1, 2, 3 dragons. However, this time there are only 14 tiles remaining because that one has been taken out of the bag. So we get 12 out of 210, which reduces to 2 out of 35. Okay. Now, what is the probability that you choose a bird and then, without replacing it, a flower? So again, we have the 2 birds, and that's 2 out of 15. And then we don't put 1 back in, so now there's only 1 flower remaining out of 14 possible tiles. And that's 2 out of 210, which reduces to 1 over 105. Okay? Now, finding the probability of a compound event, we have 1 freshman, 2 sophomores, 4 juniors, and 5 seniors that receive top scores in an essay contest. 2 students will be chosen from a hat to read their essay. What is the probability that a junior and then a senior are chosen? So the junior is 4 out of a possible 5, 6, 7, 8, 9, 10, 11, 12. And the second case would be a senior, so it would be 5 seniors out of a possible, well, 1 person has been pulled out already, so now there's only 11 remaining in the pool, and we're going to get 20 out of 132, which is equal to 5 over 33. Okay? Now let's flip it around. What is the probability that a senior and then a junior are chosen? Well, we have 5 out of 12, and then 4 out of 11, and that's 20 over 132, which equals 5 over 33. Same probability, right? It doesn't matter which order you go in, this probability is going to remain the same. Okay? The only time it would change is if you were saying something like, okay, what is the probability of a junior and then another junior happening? Well, then one of your possible outcomes has been taken away along with 1 from the total sample. All right. Now, the most real-world applications of these kind of things, especially the selecting without replacement, that would be any kind of a card game that you're playing, because when you take the card out of the deck, it is no longer possible for it to come back. And the other ones were dice-related games. The probability of 1 dice does not affect the probability of the other. Okay? All right. So for the last time this year, write down your level of understanding and write down any questions or concerns you may have over this lesson, and then write a summary over what it means to find probability of compound events. That's it. Have a great night, and then have a great summer.